Use the data booklet to help you answer these questions. DNA exists as two strands of nucleotides in the form of a double helix with hydrogen bonding between the two strands. A deoxyribose molecule in a strand of DNA is shown. Name the two types of group attached to the deoxyribose at position X and position Y. So if you look at the data sheet and you have a look at your 2-deoxyribose, then what you need to remember about your structure is that when you connect it, your sugar phosphate backbone goes down like this. Whee! This is where your sugar phosphate backbone is. And that your bases attach, so these being your bases, attached to the side of that so that they can go into the centre of the double helix. So your sugar phosphate backbone is going down the side of the structure, and then your bases are going into the middle. Okay, so X must be where there is a base. So we're looking at the data sheet, the name is base, and Y is where there would be a phosphate. There'd also be a phosphate where it says DNA strand. Then it says in the DNA double helix, adenine is linked by hydrogen bonds to a molecule in the other strand of DNA. Complete the diagram. So if this is adenine, you have to remember that adenine pairs with thymine. So we now have to connect thymine. If we go back and look at the data sheet, this is where it really helps you to be able to move that data sheet around and turn it. I'm not going to be able to do that because I've got to flick the page. But here's thymine. And remembering that adenine was already drawn for us, and adenine was drawn, it's attached to the sugar phosphate backbone via this group here. So adenine and thymine make 2 hydrogen bonds, G and C make 3. The hydrogen bonds are going from this group here, which is on one of the rings, and this N next to it. So like thinking about as far away from this attachment to the chain as possible, like as far away. They're the 2 groups that are going to hydrogen bond. So thymine is going to join to the chain, the sort of sugar phosphate backbone here, and we're going to want to go again as far away from there as possible, and we're trying to find those 2 groups that could attach. Now, so we don't want to go here because it's too close, so it's these 2. So we have to line these 2 up. This oxygen's got the lone pair and this has got the delta plus H. So the oxygen on the lone pair is going to line up to the delta plus H on this amine group, and the delta plus H on thymine is going to line up to the lone pair on this nitrogen. So it's a little bit of sort of twisting it around to join it to the DNA chain. So we're going to rotate it. We're going to rotate this molecule round anti-clockwise so that we can line it up. So that this group is going to go off to the bottom right on our original picture. So down here, because our bottom left was our DNA strand on this side, then our bottom right is going to be our DNA strand on this side. You would have your picture of thymine out next to you. I'm just trying to remember. Okay, so you would have your N with its H sticking out here. And then it went to a C with a double bond O here. And then tried to make your hexagon look a little bit better than mine. Then there was a double bond, there was a methyl group sticking off here. Then it joined back on. This, if you drew a H here, they would mark it right. But this is where the DNA strand is, okay? So this is where our DNA is. So these are the groups that are going to line up, hydrogen bonding wise. There's a lone pair on this nitrogen and a lone pair on this oxygen. And this is a delta plus H, and this is a delta minus H. And I've done a reasonably good job of allowing it to be 180 degrees. I don't think they would penalise you on this if you couldn't quite line that up. But our hydrogen bond is going to go between the lone pair on an N to the delta plus H to the lone pair through to the N, and then the same up here from the lone pair on this oxygen to the delta plus H through to the N. So 2 hydrogen bonds.